You may have seen this before, sigma notation. This has a different job. This wants to express the sum of all the terms in a sequence of a of n, which starts from a of m all the way to a of n. So a very big difference from what we had in our specific functions from the previous. We're going to use sigma and all of its individual parts that basically represent the set of possible values for a given function that's right there in the middle. Now, in sigma notation, there's going to be a starting initial value of I is equal to 1. That I, by the way, can be j, k, can be a lot of different things, n, you'll see that here in a second. But the starting value is important, as I'm sure you know from programming. But your upper limit is going to be on the very top, and it's going to tell you what to include, but stop. I bring that up only because I teach Python too, and for some reason Python, you stop at that location before it. Ugh, but anyway, I hate Python. But anyway, here is our equation like I said before. So in this, I have two different examples. We have one that's just straight up n. And notice, by the way, if these two are related in some fashion, n is going to, basically iterate with the value n that we have as our starting off value. So we're going to have n, but notice all the plus symbols in between here. That didn't come from anywhere in the function. That's right, because that's our summation. Our summation's job is to go ahead and add all the items individually from that sequence to get our sum. So that's why these magic pluses just start to show up here. So we have n starting off at 1, so that's going to be 1, and then we iterate up to 4, so we're still not there yet, then to 2, then to 3, then to 4, and then it equals 10 from that. Now, we're going to have obviously a lot more complicated than that. So let's try 1 from n to 4. N is our equation. So the 4 is going to be, as you can see, it's going to be standard throughout the entire set of our sum. But it's a value of n, literally each time it's going to increment all the way up to and including that 6 that's at the very top of our notation. So that is our sigma notation, which gets a lot more complicated here in a little bit. So a very simple example to translate something into sigma notation. First, we're going to sum the first 100 items, wow, of the sequence of a of I, where a of I is 1 over I, for I is equal to 1, 2, and all the way. So notice it gives you the starting position, gives you the equation that we're going to do. And that's really all we need, other than getting a pattern down. And again, for this one, it's easy. So it's going to be first one, if a is of 1 is going to be 1 over 1, when a is of 2 is going to be 1 over 2, and then go from there. How to translate this? We know our starting position is going to be 1. Okay? We know that our ending position is going to be 100. We know our basic formula, which is going to be 1 over I, and that's all we need to go ahead and put this into our sigma notation, which is a heck of a lot easier than trying to put it into something else. Remember, the other functions, recurrence gave us a whole bunch of sequences, and that's great. But again, if I wanted 100, you know recurrence would be a pain in the neck. You know that using the explicit function's great, but it only really gives us 1. I want to know the first 100 items, and I want to know what their sum is going to be, and we're going to deal with that a little bit later here. But very different approach to how we're doing our notation for sequences in this exact example.